Hace unas semanas empecé a darles clases a 4 estudiantes de la Universidad de La Salle, estudiantes de arquitectura. Esta universidad recibe estudiantes de todas partes del mundo, así que el idioma que tienen en común es el inglés. Por eso las clases se las doy en inglés. Hace poco tuvieron un examen de álgebra en el cual no les fue muy bien, así que dije, bueno, voy a grabar la explicación para enviárselas, así de cara a la próxima clase ya saben de qué se trataba. Así que dije, bueno, ¿por qué no subirla a YouTube? Claramente la mayor parte de mi audiencia no habla inglés. Bueno, o al menos eso creo. Así que es posible que en cuanto empiece a explicar este examen se vayan. Pero yo igualmente voy a hacer el esfuerzo en hacer unos buenos subtítulos para que, siguiendo lo que escribo en la pizarra más los subtítulos, quizás lo entiendan y puedan sacar algo de este video. La razón por la que lo subo a YouTube es porque, bueno, voy a hacer mucho esfuerzo en grabar este video y digo, bueno, ¿por qué no subirlo a YouTube? Que la gente lo vea. Quizás les cause incluso gracia el hecho de que vaya a estar en inglés, porque sí, más allá de que vengo dando clases en inglés hace tiempo, este es el primer video que voy a grabar en inglés. Vamos a ver qué sale. That being said, let's start with the video. The exam was made of 2 exercises. This one is the first. So, when we start with this exercise, the first we see is that they give us a subspace. It's called f. And the way they give us this subspace is that they give us this generic vector from which we can get a base. In the first part, they ask us to get an orthogonal basis of f. So, not just any base, an orthogonal basis. And they define this orthogonal basis as 2 vectors, b1 and b2. So let us remember what an orthogonal basis means. That means that these 2 vectors that make the base are orthogonal to each other, which means that the inner product between these 2 vectors equals 0. So, let's start with find any basis, any. And then we can use the Gram-Schmidt method to make that base into an orthogonal base, right? So, we take this vector and we want to express it as the sum of 2 vectors. In one, we want to put whatever has x, and in the other one, whatever has zeta. So, in the first vector, we get x, x, 0, because we're following these components. Look, x, right here. In the middle component, I have an x, I put it right here. And in the third component, I have no x, so I put 0. In the same way, with zeta. So, in the first component, I have no zeta, I put 0. In the second component, I have 2 zeta, so 2 zeta here. And in the third component, I have zeta, so zeta right here. So, in the next step, what we're going to do is to extract the common factor. So, in this vector, we want to extract x, and in this vector, we want to extract zeta. So, we take the scalar of the vector. What this is saying to us is that in order to get any vector of the subspace f, what we have to do is to take the linear combination of these 2 vectors, right? Let us remember that x and zeta are 2 parameters, right? So we can plug in any value in these parameters, right? So these 2 vectors are in fact the vectors that we're looking for. These 2 vectors make a basis of f. So we have a basis, but is this an orthogonal basis? Let us check. Let's see what the standard inner product is. So the standard inner product is going to be 1 times 0, which is 0, plus 1 times 2, which is 2, plus 0 times 1, which is 0. And this whole thing equals to 2. It does not equal to 0. So these 2 vectors are not orthogonal. So this is not the basis we're looking for. So what we need to do now is to make this into an orthogonal basis. And to do so, we are going to use the Gram-Schmidt method. So we have this basis made of these 2 vectors, but they are not orthogonal to each other. So we're going to apply the Gram-Schmidt method, right? So the first vector we're looking for, b1, is going to be the first vector we already have. We won't change it. But the second vector is going to be different. We are going to take the second vector we already have, which is this one right here, 0, 2, 1, and we are going to subtract the orthogonal projection of that vector onto b1. That projection is this right here. Okay, so let's plug in all of the vectors. w2 is this vector right here, and b1, which is everywhere else, is this vector right here. So, as you can see, I have already plugged in all of the vectors. Let's start computing this, alright? So, inner product. We said that this was the standard inner product, right? So, 0 times 1, 0, 2 times 1, 2, 1 times 0, 0. When we add everything, we get 2. Same in the denominator. So 1 times 1, 1, 1 times 1, 1, 0 times 0, 0. When we add that together, we also get 2. And then we have to multiply this by the 1, 1, 0 vector, right? So 2 over 2 is 1, which means we just have to make this subtraction, right? 0 minus 1 is minus 1. 2 minus 1 is 1. And 1 minus 0, 1. So this is the second vector we were looking for, the vector b2. So we have the orthogonal basis of f. It's made of two vectors, b1 and b2. The vector b1 is 1, 1, 0, and the vector b2 is minus 1, 1, 1. Let us continue with this exam. So this was just the first part. Let's go to part B. In the second part of this first exercise, they ask us to take this base and expand it to become it an orthonormal basis of R3. So let's start with the basics. To get a basis of R3, we need 3 linearly independent vectors, right? We have 2, so that means we need to find an extra vector that is linearly independent with these 2, right? So let's take it from there. How can we get a linearly independent vector? Well, my trick is as follows. I take these 2 vectors and I add them together, like that. Of course, this cannot be the vector we're looking for, right? Because it's actually linearly dependent. But I can take it from here. I can change whatever number, and that will make that vector to be linearly independent. Let's say I take this one and become it a 0. I know this won't be true. And in fact, there won't be any linear combination of these 2 vectors which can give me this vector, because I changed just one number. So this trick is fast. I have a linearly independent vector. But now I'm going to change it a little bit. I don't want this 2 here. I'm going to divide it by 2. So my third vector is going to be 0, 1, 0. So if I take the 3 vectors, b1, b2, and b3, I will have a basis of R3. But is that an orthonormal base? Let us remember what this means. Orthonormal is not the same as orthogonal basis. In an orthogonal basis, we want that the vectors of the basis are orthogonal to each other. But when we say orthonormal, we want even more. Besides that, we want the vectors to have length 1, alright? But let's take it step by step. First, let's make sure that the vector b3 is orthogonal to these 2 vectors. Let's see if that happens. Let's calculate the inner product. Let's start with the inner product of b1 and b3. So when we do the math, we get 1 times 0, 0, 1 times 1, 1, and 0 times 0, so 0. When I add them together is 1. Doesn't equal to 0. So these 2 vectors are not orthogonal. So that means that I have to apply the Gramsci method again so that I can change this vector and actually find a vector that is both orthogonal to b1 and b2. So we have this vector and we realize that it's not orthogonal to vector b1. And if you do the math, you will realize that it's not orthogonal to b2 neither. So what do? Again, Gram-Schmidt method. We want to find a vector b3, that is orthogonal to both b1 and b2. So b1 and b2, we won't change them, right? Because we just want to expand the base. So we need to add a third vector. And in order to find that vector, we take the vector we already have and we subtract both the projection of that vector onto b1 and the projection of that vector onto b2. Both orthogonal projections, right? So let's plug in the vectors we know, right? w3, b1, and b2. Like this. First, take a moment, pause the video, and make sure you understand how I replace the values, alright? w2, b1, and b2. Once you do that, let's continue. Let's compute the calculations here. So here, in the product, I get 0 times 1, 1 times 1, 0 times 0. We add that together, we get 1. Then here, 1 times 1, 1 times 1, 0 times 0. We add that together, we get 2. Let us continue here. 0 times minus 1 is 0. 1 times 1 is 1. and 0 times 1 is 0. We add that together, we get 1. And then we get minus 1 times 1 is 1 is 1, 1 times 1 is 1, and 1 times 1 is 1. We add that together, we get 3. So, vector b3 is going to be, for the first component, 0 minus 1/2 multiplied by 1 minus 1/3 multiplied by minus 1. If we do the math, we get minus 1 over 6. For the second component, we get 1 minus 1/2 times 1 minus 1/3 times 1. So if we do the math, we get 1 over 6. And for the last component, we have 0 minus 1/2 times 0 minus 1/3 times 1. So that is minus 1 over 3. What we just got is a vector b3 that is orthogonal to both b1 and b2. So this is an orthogonal basis of R3, but we were asked to find an orthonormal basis. So that means we have to go one extra step ahead, right? All we have to do is to make these three vectors, b1, b2, and b3, into unit vectors, which means that their length has to be 1. So, as I said, if we have a vector and we say that that is a unit vector, then the length equals 1. We calculate the length by doing the square root of the inner product of that vector with itself, okay? So let's calculate the length of the three vectors we have, b1, b2, and b3, as follows: square root of the inner product of the vectors with themselves. With b1, we get the square root of 2, with b2, we get the square root of 3, and with b3, we get the square root of 6 over 6. So, obviously, they're not unit vectors. These are not 1, right? So we have to turn them into unit vectors. And to do so, we just take the vector and we divide it by its current length. So that means that in order to get the unit vector b1, which we write like this, what we have to do is this operation. So in this particular case, we get this operation, right? So we have to do 1 divided by square root of 2, 1 divided by square root of 2, and 0 divided by square root of 2. And we get this vector right here. If we do the same with vector b2, we will have this unit vector right here. And also, if we do with the b3, then we will get this vector right here. Minus 1 divided by the square root of 6, 1 divided by the square root of 6, and minus 2 divided by the square root of 6. So now you can go ahead and check. These three unit vectors are orthogonal to each other, which means that the inner product between them is 0. And also, each of these vectors are unit vectors. So if we take these three vectors and put them together, they make an orthonormal basis of R3, which is what we were required to do, right? This, let me say, was the easy part. Nothing too weird about it, alright? So now is when it gets interesting. The next things they will ask from us can be either easy or really hard. That depends on the approach we take. I hope you're ready, because your brain is about to explode. Why is that? Because here we have, which apparently is a really hard exercise, but if we approach it the right way, it's so easy. Let me show you. What is this asking? They're asking for us to find a subspace G, to give a basis of it, and to give the dimension of this subspace, okay? What is G? So G is the intersection of two subspaces, these two right here. The first one is the orthogonal complement of the subspace generated by B1. And the second one is the orthogonal complement of the subspace generated by B2. What is orthogonal complement? Let us remember that. So if we have the orthogonal complement of a subspace S, that means if we take any vector belonging that subspace and we take any other vector belonging to S, these two vectors must be orthogonal to each other. For example, if we are in R3 and S has dimension 2, S is in fact a plane, right? And the orthogonal complement will be a line perpendicular to that plane, which means that here we have 90 degrees. So if we take any vector whatever vector we want from S, it will be orthogonal to whatever vector we want from the orthogonal complement. That's what that means, okay? So, knowing that, having that concept really clear in our heads, we can actually realize that this is really easy. Let's take a look at this again. This is asking for us to find a subspace that makes two conditions, right? First condition, any vector of G has to be orthogonal to V1. And also, any vector of G has to be orthogonal to V2. So orthogonal to both V1 and 2. So we can rewrite this as the orthogonal complement of the subspace generated by both V1 and V2. Because that way, any vector of G has to be orthogonal to both V1 and V2. And this should be more familiar to us, right? What is that subspace? What subspace do we get when we make the linear combination of V1 and V2? Well, let us remember that the base of F is made of these two vectors, right? So the subspace generated by these two vectors is in fact F. And now, this is not that tricky. All we want to do is to find the orthogonal complement of F. So let us think of what aspect should the basis of G have. What is the dimension of F? Well, the basis of F is made of two linearly independent vectors, right? So the dimension of F is 2. Let us remember too that the sum of a subspace and the orthogonal complement of it is direct, which means that the dimension of the intersection is 0. So since G is the orthogonal complement of F, the dimension of the intersection of these two subspaces is 0. How is this useful? Well, let's use the Grassmann's rule. Grassmann's rule says that the dimension of G plus the dimension of F minus the dimension of the intersection should be the dimension of the sum. We said that the dimension of the intersection is 0 because they are in a direct sum. We know that the dimension of F is 2. And since we are in R3, we know that G plus F is R3. Let's remember, when we take one subspace and we add the orthogonal complement, we get the whole subspace, right? So we get R3. And the dimension of R3 is 3. So if we take a look at this, we have an equation that will allow us to get the dimension of G, right? The dimension of G should be 1. So we have the dimension of G. Why do we want the dimension of G? How is that useful? Well, if we know that the dimension of G is 1, then we know that its base is made of one vector. What vector? Well, since G is the orthogonal complement of F, any vector of G should be orthogonal to any vector of F. So, any vector of G should be orthogonal to the vectors in the basis of F. Do we know a vector that is both orthogonal to V1 and V2? Do we? Of course we do. This vector right here. We know that this vector is both orthogonal to V1 and V2 because this is in fact an orthonormal basis. So this vector right here could be the basis of G we are looking for. And we are done. We have the basis, we have the dimension, and we had to do nothing basically, just apply concepts. If we hadn't realized of that, we should have had to do a lot of calculations. Starting with looking for the subspace, and then to look for this one, and then to do the intersection, and then to find a basis. A lot of time in an exam, right? This way, applying concepts, it was pretty straightforward, right? Even more, in the next question of this exam, they will ask us, is G a direct sum with F? Now we know, of course it is, because we already realized this relation right here, that G and F are orthogonal subspaces to each other. And then by definition, of course, they are direct sum, which we represent with this, right? So we have two C and D made really, really fast applying concepts. For the last part of this first exercise, they give us a vector E1 which is the vector 1, 0, 0, and they ask us to find both the orthogonal projection of that vector onto G and onto F. Let's start with G because it's way easier. If we want to find the orthogonal projection, we just have to make this with every vector of the base. So since G has just one vector, right, B3, we have this. If we decided to begin with the orthogonal projection onto F, then we will have this with B1 and also with B2. So this is way shorter, right? Even more, since B3 is a unit vector, that equals to 1. So let's just worry about the rest of the expression. Let us start here. So let's plug in E1 and B3. So here we have the inner product, right? So we have 1 times this, 0 times this, 0 times this. Let us don't worry about this, right? It's 0. So 1 times minus 1 divided by the square root of 6 is minus 1 divided by the square root of 6, which now we have to multiply by this vector, right? And now we just have to compute a product, right? So we have minus 1 divided by the square root of 6 times every one of the components. And here we have the projection of the vector E1 onto the subspace G. Now we have to find the projection of the vector E1 onto the subspace F. But we are not going to do it the same way. It's going to be a lot of math, and there is an easier way to do it. And that is because we realized before that G and F are orthogonal complements of each other. It becomes really easy to find the second projection we need when we remember that any given vector can be made of the sum of two vectors. The projection of that vector onto a subspace S and the projection of that same vector onto the orthogonal complement of the subspace S. In our example, S, we can say that it's G, and the orthogonal complement, we can say it is F. We already have this, right? So we can say that the projection of E1 onto F is made of this subtraction. We know both vectors, right? E1 is the vector 1, 0, 0, and this projection, we just got it. So when we plug that in, we get that the second projection we're looking for is this vector right here. 5 over 6, 1 over 6, and minus 2 over 6. This first exercise is the perfect example on how we can solve things differently in an easy way if we remember the concepts. If we just stop memorizing formulas without actually understanding them. I encourage you to always think what you're doing from a conceptual point of view. Stop focusing on the computing and start focusing on the underlying concepts of every subject. There is a second exercise to this exam, but I just realized how hard it is to record in English. So for that second one, I'm just going to chat with my students and solve it differently. Y les agradezco a todos muchísimo por estar viendo este video, más allá de que quizás muchos no entendieron mi inglés, porque bueno, digamos que tampoco es perfecto. Y ha sido un reto, ha sido un gran reto explicar algo con lo que me siento súper cómodo en un idioma que no domino perfectamente. Bueno, espero que les haya gustado y nos vemos en el próximo video. Bye.